So this is liquid known as solvent extraction. So the reference for this particular side is our two reference books, John Couples and McCabe, and of course your handbook, your Paris handbook. So we'll start with the intro to liquid extraction, and we need of course to define the process. So when we speak of liquid or solvent extraction, it's a process for separating the components of a liquid, that is the feed, by contacting it with another liquid, that is the solvent, with the two phases being chemically different. So in this case, we don't have a gas and the liquid phase being contacted, but rather we have both of the phases as liquid. Okay, one is the feed and the other one is the solvent. Okay, let me again share. Can you see now the slide on liquid extraction?
Yes, Miss.
Okay. So in here, the transfer of the components is from one phase to the other, and it's driven by the deviation from thermodynamic equilibrium. Now, separation is according to the difference in the physical and chemical properties. Now, one of which would be the differences in the polarity of the two liquid phases. Another one could be the water loving or water heating character of the feed and the solvent itself. So the hydrophobic or the hydrophilic character of the phases. Now, in the manner of contacting these two liquid phases, the feed and the solvent, we produce also two phases. Now, the one that is that we are in mostly interested in would be the extract phase that contains the portion of the feed that was taken out from it, and then an extracted feed stream we call as the raffinate. So the raffinate is not really, we're not really interested with the raffinate, because if our component of interest is really present in the raffinate, that would be in just a very negligible or small amount. A majority of the component that is taken out by your solvent from the feed goes with the extract. So the phase that we are most interested in here is the extract. So again, initially we contact two liquid phases, the feed and the solvent phase, and it's producing two phases as well, and that's the raffinate and the extract phase, both of which are liquid in nature. Now, what are the specific applications of liquid extraction? So we have the removal of acetic acid from water. Now, if we want to remove acetic acid from water, then we can use an organic solvent to do that. An alternative to this process is distillation, but you know distillation is really costly. So that is why they'd rather use a certain organic solvent to take out the acetic acid from water. And of course, recycle the extract later by reusing the same organic solvent. But for those processes that needs high purity of extraction, they may use distillation. Of course, with the additional cost. Now, another application is the removal of high molecular weight fatty acids from vegetable oil. Now, again, organic solvent is being used here. So propane is the solvent and it's organic. And another alternative that can be used here is high vacuum distillation. If distillation is costly, then high vacuum distillation is even more costly. So that you have extraction as an alternative in this case. Now in here, you have the recovery of the desired component, which is the high value fatty acid or the high molecular fatty acid. In the case of the previous example, your liquid extraction is used in removing a certain contaminant. And in here, we view that acetic acid is the contaminant because we separate it from water, or we take it out from the water that contains it. Okay, another one is the separation of penicillin from complex fermentation mixtures. So after the process of fermentation, penicillin that is being used in the production of drugs can be separated from the other components in the mixture using liquid extraction. In here, you have the recovery of the desired component as the objective. So your desired component is your penicillin. Another one is the metal separation of aqueous solutions of copper iron, uranium vanadium, and tantalum columbium metal pairs. So if you want to take or separate these metals in their solution, then we can use liquid extraction. Of course, using a solvent that is highly affinated to just one of the metals that are in this mixture. So for example, you look for a solvent that is highly affinated to iron. So you'll be able to take out iron from the copper iron mixture. So in this case, your objective is to separate iron, or let's say to separate copper from iron, whichever of the two you considered as the contaminant. So the same applies with the mixture of uranium and vanadium and tantalum and columbium. You look for a solvent that is highly affinated to just one. So then it will only be taking out that particular component that it is affinated to, separating the two now. So as such, you were able to do the separation. By the way, in the slides, you could see the sections in the handbook where you can read on the examples that are specified in this particular slide. Now, there are two main classes of solvent extraction equipment. So we have a very simple vessel with a form of some form of agitation, mechanical agitation as one that could separate the components. Another one, we can have vessels in which mixing is done by the flow of fluids themselves. So oftentimes we're using the second one, this one, wherein you have the mixing of the fluids is due to their velocities. The fluids that I'm referring to in here is your feed and your solvent. Now, so that's it. When we speak of solvent extraction, we take out a component from a feed using a solvent, which will be responsible of separating that component from the rest of the mixtures in the feed. The separated component goes to the extract. The other components are in the raffinate. Okay? Though we don't, of course, just like in any processes, we don't view a 100% separation. But in this case, liquid extraction is an option that is less costly than the distillation process or the highly costly version, which is the high vacuum distillation process. Okay, now it's less costly because we can actually recycle the solvent that is being used. Okay, now we go to the definition of terms. So we have the feed. So our feed is the solution that contain the components or components to be separated, and it constitutes the solvent, or we refer to it as the carrier solvent and the solute. Now, how do you know that A is the solute and B is the carrier solvent? So the component that is present in the least amount in your feed is your solute. So if it's just, let's say, present in just 1% or 2%, then that's your solute. The rest are viewed as your carrier solvent. So it's the major liquid component in your feed. Okay. Now, more on the definition of terms. So there are terms here that you will be encountering in the process of liquid extraction. And it's very important that you understand these terms as well. You can find this as well in the handbook. So when you speak of the extraction solvent, we are referring to the separating agent, the one that is responsible for the separation, the actual separation. So it is the immiscible or partially miscible liquid added to the process. So it could be miscible, 100% miscible, forming a 100% homogeneous solution with your feed, or it could be only partially miscible with the feed. Now, its purpose in being added to the feed is to create a second liquid phase for the purpose of extracting one or more solutes from the feed. Though to the fact that if we have more solutes to be extracted, that would be more complicated to process, we are limiting all our extraction problems here to single component extraction only. We take out, let's say, component A from the feed. Now, we don't cater to problems in here which have several components taken at one time from the feed, because that would still entail further separation. Because if you view unit operations, if you have to deal with just one particular component, then there's a much needed need. There's a need for more processes to follow. That way you be able to separate that component that you are most interested in. Okay. Now, our extraction solvent, our separating agent, can be comprised of the extractant, dissolvent, and liquid diluent. You have this extractant, which is dissolved in the liquid diluent. Your diluent in your separating agent is comparable to your carrier solvent in the feed. The extractant is comparable to the solute in the feed. So the one responsible of taking out the solute in your feed is really the extractant. The one that carries it in your separating agent is your diluent. Now we can have an added component we refer to as the modifier. It is being added to your diluent to increase the solubility of the extractant or otherwise enhance the effectiveness of the extractant. So the purpose of the modifier is to improve the characteristic of the extractant to take out the solute from the feed. Okay, but in most cases, our separating agent, our extraction solvent is just made of the extractant and the diluent. It's only in special cases wherein we have the modifier. Now in here, we also have what we call stages. So we have stages in distillation, we have stages in gas absorption. Okay, in multiple effect evaporation, the stages that we're talking about could be comparable to the effects itself. So in here, we also have what we call equilibrium stage, or we call it the theoretical stage. So this is the device or a combination of devices that accomplishes the effect of intimately mixing two liquid phases until equilibrium concentrations are reached, then physically separating the two phases into clear layers. So the real mass transfer occurs in the interface. And where is this interface produced? In the bulk phase. Where does the bulk phase happens, or when is this bulk phase formed? It's in the equilibrium stage. So it's the one that accomplishes the goal of intimately contacting the two liquid phases. Now, only when equilibrium is reached, when actual mass transfer ceases. So there won't be any mass transfer. It's not that there is no flow or from one phase to another or vice versa, but it's just that there is no net flow of your solute from one phase, that's from the feed, to your extract phase. Now we have the extraction factor. So the ratio of the slope of the equilibrium line with the slope of the operating lines. Again, we have operating lines in the previous unitary processes discussed. In here, we also have that. And we also have the equilibrium line. So, or it could be the flow rate of the feed divided by the flow rate of the solvent. The flow rate of the feed, the phase that contains the component of interest, divided by the flow rate of the separating agent or your solvent. Now, what about separation factor? So your separation factor is analogous to relative volatility in distillation. So if distillation, in a sense, is checked whether it's feasible or not by determining the relative volatility, and its value has to be greater than 1 for separation to occur, in here in extraction, it's the separation factor that we determine. Now, what about this K? Now, McCabe is using K in the various example problems regarding extraction in McCabe. So it's the partition ratio, or the distribution constant, or the distribution coefficient. All of this refer to this letter K. Partition ratio, distribution constant, or distribution coefficient. Now, that's the solute concentration in the extract phase divided by that in the raffinate phase. Take note of this after equilibrium is attained in single stage of contacting. So it's not just any particular concentration in the extract divided by concentration in the raffinate, but it's the concentration at equilibrium. And this is what we call as the distribution coefficient. This is the most commonly used term to refer to K, the distribution coefficients. Now, for dilute systems with straight operating lines, this partition ratio K is equal to the slope of the equilibrium line itself. So your M for your equilibrium line is the K for dilute systems. Again, what are these dilute systems? These are systems in which the concentration is less than 10%. Please refer to this section in your handbook and to this table because the table gives you the different distribution coefficients for the systems that are indicated. So check the sections that are being referred to in the slides that are emphasized in the slides here. Now, what about these solvent properties? So what are the properties of our solvents that are very important in terms of its capacity to accomplish the extraction or the separation? So we have number one, the loading capacity. So it's the maximum concentration of solute the extract phase can hold before the two liquid phases can no longer coexist or solute precipitates as a separate phase. Loading capacity, the maximum amount of solute that your extract phase can hold. If it has more solute that it can hold, or if it has more solute than what is indicated by its loading capacity, crystallization starts to happen. So it's when the solute precipitates as a separate phase in your extract phase. And as such, you'll be forming solids rather than liquids already. Okay, so that's your loading capacity. Your partition ratio that was referred in here is the same partition ratio in here. I just added something and added information here. Now you could see that the formula is y sub I over x sub I. Now high partition ratios generally allow for low solvent use, so meaning a high value of K requires smaller amount of solvent to use, smaller and less costly extraction equipment utilization, and lower cost for solvent recovery and recycle. So the higher the value of the K, the more cost effective is your process. Because you have low solvent use, you have smaller and less costly extraction equipment utilization, and lower cost for solvent recovery and recycle. So what is the value for the K? Synonymous to relative volatility in distillation. So if alpha in distillation should be greater than 1 for separation to proceed in here, K should be 10 or higher so that your extraction process is cost effective. Okay, you'll be saving more in the solvent. That's for the partition ratio. Now, more on solvent properties, so solute selectivity. I think this is already a given. Now, it is very important not only to recover a desired solute from the feed, but also to separate it from other solutions or solutes present in the feed and thereby achieve a degree of solute purification. Your solvent, as much as possible, should be only affiliated to the solute so that you won't need other separation processes, further separation processes just to isolate your solute further from your extractant. Okay, it's stated here. The selectivity of a given solvent for solute I compared to solute J is characterized by the separation factor with the same representation as the relative volatility in distillation. So it's alpha sub IJ, and it's actually the distribution coefficient in terms of I divided by the distribution coefficient in terms of J. So what is this K? Remember, K is Y over X. So this is YI over XI divided by YJ over XJ. That would be for the separation factor or the selectivity of solute I compared to solute J. Now, values for selectivity must be higher than 1, just like distillation, to achieve an increase in solute purity on a solvent-free basis. Now, what about mutual solubility? So low liquid-liquid mutual solubility between feed and solvent phases is desirable because it reduces the separation requirements for removing solvents from the extract and raffinate streams. What this means in class is that the carrier solvent of the feed and the diluent of your separating agent should not be also completely miscible with each other. Or shall I say, they should have low liquid-liquid mutual solubility. Because if that is the case, if you want to isolate one from another, you'll be needing more separation, further separation processes in your system. So low liquid-liquid mutual solubility between feed and solvent phases is desired because it reduces the separation requirements for what? Removing solvents from the extract and raffinate streams. We want the solvents as well to be not completely miscible with each other. Now, stability. So solvent should have little tendency to react. We're not considering here separation with reactions with your product solute and form unwanted byproducts, causing a loss in yield. So it should be a pure physical separation. There shouldn't be any chemical transformation. Also, it should not react with feed components or degrade to undesirable contaminants that cause development of undesirable odors or color over time, or even cause difficulty achieving desired product purity or accumulate in the process because they are difficult to purge. Okay, they remain in the process and their amount keeps on increasing because it's really difficult for them to be separated. Now, viscosity. This is very one important thing to consider in separation, especially in extraction. Low viscosity, hindi dapat lapuyot, is referred since higher viscosity generally increases mass transfer resistance. The more viscous your phases are, the more difficult for the solute to be separated from the rest of the carrier solvent that it is with in the mixture in your feed. And liquid-liquid separation in this case is difficult. So we want the phases to be as much as possible less viscous, or if not at all viscous. An extraction process can be operated at an elevated temperature to address viscosity problems, where viscosity is significantly lower. So if we increase the temperature, viscosity lowers for better mass transfer performance, even when this results in lower partition ratio. So gagamay mo partition ratio, but better because you can your feed becomes less viscous. That is, the process is operated at elevated temperature. So we increase the temperature, that way it will not be very viscous. Now, recoverability. So I have mentioned this several times already. It is very economical and it is suggested that your solvent can be further reused. So the economical recovery of your solvent from the extract and raffinate is critical for commercial success. It's not something that it's just a one-shot deal. As much as possible, we want our solvent to be recycled and reused. Now, what about density? So we have talked about viscosity a while ago as a hindrance to mass transfer. So density difference, a difference in density between the solvent and the feed phases in the order of 0.1 to 0.3 gram per ml is preferred. So in terms of the density of the feed and the density of the solvent, the difference of their density should be within this range, 0.1 to 0.3. A value that is too low, meaning lower than 0.1, makes for poor or slow liquid-liquid phase separation. Hinay ang pag-separate and may require use of a centrifuge. And that would be added cost. Now, a value on the other hand that would be too high, meaning higher than 0.3, makes it difficult to build high dispersed droplet population density for good mass transfer. That is, it's difficult to mix the two phases together. if the difference in the density is higher than 0.3. And if this happens, the manner of maintaining a high hold up of dispersed phase within the extractor will be difficult. Why? Because it depends on the viscosity of the continuous phase. So this time, we have to look into the viscosity already of the continuous phase. And what is this continuous phase? That is our feed. So if we have continuous phase and gas absorption referring to the feed gas, in here, the continuous phase is also our feed in extraction. So that is in terms of density difference. So take note of the range of the difference in the densities. Now, solvent properties, more on it. So safety, solvent with low potential for fire and reactive chemistry hazards are preferred as inherently safe solvent. So we want it to be non-toxic and low potential for fire and reactions. Okay, further reacting with other components in your liquid phases. Interfacial tension. So preferred values for interfacial tension, we had this thing also being considered in the design of our gas absorption and stripping columns. Now, the preferred interfacial tension between the feed phase and the extraction solvent phase generally are in the range of 5 to 25 dyne per centimeter, or 1 dyne per centimeter, which is equivalent to, rather, 1 dyne per centimeter class is equivalent to 0.001 Newton per meter. Now, with interfacial tension that is not within this range, meaning either lower than this or higher than 25, systems with lower value. So for this one, lower than 5, so 4. For example, the system will emulsify. Do you know what emulsify is? Do you have any idea what's emulsify? What do we mean with emulsify? So if we have a low interfacial tension between our feed and extraction solvent, what do you mean by emulsify? Anong matabo if the interfacial tension is lower than 5? You can write your answer on the chat box. Emulsify. What does it mean, emulsify? Any idea? Emulsify. That's basic term. That's a basic term. Emulsify. Thicken. Ma-mix, ma-thicken. Okay. Isa is correct. Thicken. When do we form thickened solutions, by the way? Or thickened, not solution. When the mix of two solutions or phases thickens, what is being formed? Mag-thicken siya? Or there's a better term. Thicken, not ma-mix because we know nga ga-mix magina sila. Kaya kung hindi na sila mag-mix, wala ta mas transfer. Our goal is really for them to mix, to form the bulk phase, that we will have the interface where real mass transfer occur. But we don't want them to be viscous, very viscous. We don't want them to have less or high density difference in the one discussed a few minutes ago. And we don't want them to have low interfacial tension. I'm referring to the feed and the extraction solvent. What do we mean by emulsify? It's a standard term, but it's a common term. What happens when liquids emulsify? Emulsification. No idea? Colloidal mixtures emulsify. Emulsify, just like in the case of the mayonnaise, that's a process of emulsification. The process of forming mayonnaise, it's a colloidal mixture, that's emulsification. So we don't want that to happen. So as much as possible, our interfacial tension for the feed and the liquid phases should have an interfacial tension of higher than 5 not greater than 25 dyne per centimeter. What about if it's higher than 25? Let's say it's already 26 or 30. For systems with higher values, dispersed droplets tend to coalesce easily, resulting in low interfacial area and poor mass transfer performance. Unless your system has some form of mechanical agitation. So what do we mean by this? Okay, higher values will form coalesced dispersed droplets. In our language, if you allow me to use the vernacular, magsining ka coalesce, ang droplets, mga separate dapat, coalesce, nagtapikanay sila. So if they will form one lump, if these dispersed droplets won't remain dispersed, but rather they will lump themselves together, then interfacial area is decreased. If interfacial area is decreased or surface area is decreased, then of course mass transfer is decreased. So that's our problem. We don't want low interfacial tension to prevent emulsification. We don't want high interfacial tension for a decrease in the interfacial area. There is, though, an alternative that could be done if it could not really be avoided, that you have an interfacial tension higher than 25 dyne per centimeter. But if you will practice solving problems in John Couples and even in McCabe, the interfacial area is most of the time 20-25. It's not greater than that. It's because of this particular important solvent property. That's the interfacial tension. Okay? I think we're almost ending with the solvent properties. Industrial hygiene. Industrial hygiene. So this has something to do with the how toxic our solvent is. So solvent with low mammalian toxicity and good warning properties are desired. Low toxicity and low dermal absorption rate reduce the potential for injury through acute exposure. I think this is self-explanatory. So dapat hindi siya toxic. Now, as to freezing point, this is a concern for those in the western part of the globe where they have when they have winter. So solvents that are liquids at all anticipated ambient temperatures are desirable, meaning they should have they should not get frozen easily. Since they avoid the need for freeze protection or thawing of frozen solvent prior to use. Because if they get frozen easily, then there's a need for thawing before to using it or prior to using it. Okay. The multiple uses in terms of solvent properties is more on the economic side. So we want as possible our solvent to be recoverable, recyclable, and can be reused further in the other parts of process. Pero may ara, bidyang specialty solvents maybe that cannot be used or reused in other parts of the process. What is just important in here is that it could be recovered and as much as possible reused in your system. With just, of course, the requirement that its purity, so if it's recycled already, we don't expect its purity to be the same as that one which is freshly bought. So in terms of purity, you want to enhance its purity by, of course, taking out contaminants from it. So that would be added cost. Or maybe you can mix it with the new one as long as the purity of the mixture already is still acceptable in terms of process requirement. Okay? So ang requirement gini permi nga dapat makasave ang isa ka process as much as possible. Now, environmental requirements, of course, this has something to do with everything to be sustainable, with life being able to sustain itself. So solvent must have physical or chemical properties that allow effective control of emissions from vents and or other discharge streams. So you should be able to control the emissions or address the quality of these emissions. Probably if they are not ready for discharge yet, they need to be processed. Anyway, you will learn that, or probably you have learned that already in your waste pollution treatment. Okay. Now, preferred properties include low aquatic toxicity. It's a given. It should be non-toxic to the living organisms in water bodies where it should be dispensed, and low potential for fugitive emissions from leaks or spills. Fugitive emissions meaning emissions that are not easy to, shall I say, keep track of, or in our language, hindi mo siya dahil wala fugitive. What's a fugitive? Hindi siya madakpan. So we want emissions that can be easily contained. So there's the leaks or spills that could be easily contained. Okay. It is also desirable for solvents to have low photoreactivity in the atmosphere and be biodegradable. So it does not persist in the environment. Again, with sustainability as, of course, in terms of the environment. Materials of construction for your equipment, it is desirable for a solvent to allow the use of common, relatively inexpensive materials of construction at moderate temperatures and pressures and availability and cost. So as much as possible, we don't want it to be very costly, and as much as possible, we want it to be locally available. If not, having it in the warehouse or having it in stock at all times requires, of course, cost, because your money stays with it, especially if it's imported. So you have to consider lead time in the procurement of the said solvent. The solvent should be readily available at a reasonable cost. So considerations include initial field cost, the investment cost, so associated with maintaining a solvent inventory in the plant. So since if you're importing it, you don't know any concerns that you may be encountering in terms of importation. So you have to maintain a certain amount of solvent inventory. And keeping that amount of solvent in your inventory entails keeping money there. Wait, not being used, it's just there, just to ensure that you have ready amount of solvent should there be any problem with importation, if it's not locally available. Okay, all of this you may think, why so many? Because you can all find this in your handbook, so that is why I place it in here. Now, we go now to analysis, extraction, liquid-liquid solvent or liquid-liquid extraction equations to use, especially when we do material balances concerning the operation. So in here, we have three components. So we're so used with just two components. We just have A and B so far in all our unitary processes that we have discussed. It's just A and B. Now we have C. And you have to know what is this A, B, and C in view or in association with the process of extraction. So this is it. I'd like to emphasize it. A is your solute. That's the component that you are interested in, mostly interested in. B, most of the time, is water. Okay, B is water. And normally, this water is your carrier solvent for your feed. So the one that carries A is the B. So that's your B. What about the C? C is your solvent, the extractant, the one that is responsible in taking out A from the feed. So these ABC components are all present in your equilibrium diagram. So unlike the other processes that we have covered so far, the components that are present in our equilibrium diagram are only two. It's just either A or B. So with A and B present in all phases, or A present in one phase, B in the other phase. In here, we have three phases now. That will be all present, that are all emphasized in the equilibrium diagram. So one may be unimportant, and that unimportant component is the B, which is the water, but it's very important that you should understand that A is the solute and C is the solvent, the extractant specifically in the solvent. Now, your very important variables here in the operation that would be very important in considering how your operation will How will your extraction perform? Will be temperature, pressure, and of course, concentration. These are your operating variables, temperature and pressure. As always, very important for any unit operation processes. Now, whether we speak of XA, XB, and XC, the sum of these three in your particular phase should be always equal to 1. So A, B, and C should always be equal to 1. Or YA, YB plus YC, YA plus YB plus YC should always be equal to 1. XA plus XB plus XC should always be equal to 1. Okay, X is for your feed, Y is for your solvent. Okay, I just place here X for the feed, but the Y representation of concentration is for your solvent. Now let me proceed. So I've mentioned a while ago that in extraction, you have three components that are present in your equilibrium diagram. Okay, in our previous equilibrium diagrams, you only have A there. We're not interested with B even. It doesn't appear here. But in here, you have 3. Now, in here, in the horizontal axis, you have 0 mass fraction of B to 1.0 mass fraction of B. So this is 100% water at this point here. Okay, let me just use the, let me check this one. That's your water. Okay, that's your water there. 100% water, 0 water here on the left side. Now, as we go from this side down, going up to the apex of this triangle, you see here mass fraction C. So you have 0 C and you have 100% C in here. So meaning at this portion here, you have 100% solvent, extractant. Okay, the one that is responsible for taking out A in your feed. Now, from the tip of this triangle going down to the lower left side of your triangle, you have 100% A, and this is your solute here. 100% A, and that is your solute. We read the mass fraction here in the horizontal axis in this manner. Pahilay siya, class, parallel to this side of your triangle. Okay, so this is 0.2, 0.4, 0.6, 0.8, and you have here 100%. As for the C, it's horizontal. So you have 0.2, 0.4, 0.6, 0.8, and then 100% C. Horizontal. As for your A, so this is your A, you have 0 A here on the tip of your triangle to 100% A here at the bottom. So it's the scaling is parallel to the right side of your triangle, this side of your triangle, the inclined side, the right inclined side of your triangle. Okay. So at this particular point M here, we say that our system has, so in this case, 20% water, 40%, whatever is the solvent, it's not indicated, and 40% A. So that's how you read the concentration. So for M, it's 40%, no, sorry, 20% B, 40% C, and 40% A. I hope you get it on how you're going, on how to get the concentration. And so far, we've been dealing with mole fractions, okay? Mole tanan, mole fractions in terms of mole. Now with extraction, we change it to mass fraction. So when you speak of recovery in extraction, has something to do with recovered mass, not moles. Okay? Now we proceed if there aren't any questions. Again. Now in here, you can find this in section 15-26. This is another triangular diagram in the case of partially miscible components of your feed and solvent. So you have now this formation of a one-phase region and a two-phase region. So this in this particular region, you have one homogeneous phase. If the concentration falls in this particular area, then you have one homogeneous phase. If it falls anywhere here under the phase envelope, we call this curve here as the phase envelope, then we have a two-phase region. Okay, that's a two-phase region. You have this bulk phase M in the center, and this is your A and B connected by these tie lines. I will explain the tie lines later when we go to a bigger diagram. This is the plate point here. The plate point is that point wherein there won't be any separation anymore. That will occur in your feed phase and in your extract phase. Extract phase, solvent phase. So there won't be any separation already at the plate point, PLAIT. Now that's how it looks like if you have partially miscible components. Now, when we speak of extraction class, we're so used that when we use equilibrium diagrams or correlation diagrams, isa lang ka-curve ginatanaw ta, and then we just one particular, not curve, just one particular partition plane with several curves in there. Now, in the case of extraction, we have two shall I say, equilibrium relationships that are being connected to each other. You will see later. I think it's in here. Before I discuss this table, I'd like to go to that. This is what I'm referring to. So we're so used to only having one diagram for a particular unitary process. In extraction, we have two. You have here in this particular rectangular diagram, the relationship between your water layer, your raffinate composition that is horizontal, and then the ether layer, which is your extract composition. This is water layer. This is the raffinate layer. This is extract layer, and this is your ether layer. This is in the case of acetic acid, ether, water solution. Your acetic acid is the A, your C is the ether, and your B is of course water. So in terms of a diagram to use, an equilibrium diagram to use for extraction, they really come in pairs. One that gives you the relationship between the composition of acetic acid, in this case, A, in both the raffinate and the extract layer. The raffinate is the horizontal axis here in this rectangular diagram, and the extract layer is the vertical axis, all giving you the relationship between compositions of A in these two layers. So XA for raffinate composition, YA for extract composition, all in A. So comparable to an equilibrium relationship in gas absorption. You have XA in the liquid and YA for the gas. Ang kinalain lang nila sa extraction kay diriya, wala ta diya moles, mas na diya. And then we have the raffinate and the extract layers that are now being considered. What are these two layers? These are actually the product layers after your feed and your solvent phases were already contacted and A was taken out or extracted by your solvent from the feed. So this is it here in the lower part. Okay. Now, what about this upper part? What do you have here? In the upper part, you have mass fraction of A on the horizontal. But the mass fraction in here, class, could be either in the liquid phase or in the feed phase or in the solvent phase. You could see here it's either XA or YA here in the horizontal. While in here in the vertical, it's now C. It's now your extractant C. So either in the feed or in the solvent itself. So X is for the feed, Y is for the solvent. It has subscript C because it's the composition of your extractant C. In here, it has subscript A on the horizontal axis because it gives you the concentration in terms of A, the solute in the feed. Okay, so again, you could see here, this is the curve actually below. This is the curve. I'd like to use a smaller one. Wait lang. This is the curve. Oh, di na makontrol ka. Now, this is the curve that gives the relationship between XA and YA. Concentration of A in the raffinate and here in the extract. Well, in here, on the upper diagram, you have this one, the relationship between XA, XC, YA, YC. Okay, now it's now concentration of A and C. Where? Either in the feed or in the solvent phases. Now, this is still your phase envelope, the same phase envelope that I referred to in the triangular diagram, separates the one phase region. This is the one phase region here on the right side, and the two phase region is the region enclosed by the phase envelope. Whenever we plot, that is, if we do graphical approach, whenever we plot on this particular set of diagrams, the extract layer composition should always be, the extract phase should always be on the upper part. It always appears on the upper part of this phase envelope, and the raffinate is in the lower part. You will understand it better when we go to specific examples. Pero kung mag-plot kita, class, ang extract, permi na siya sa babaw, sa phase envelope. Ang raffinate, it's on the bottom part of the phase envelope. Okay? Now, what is the relation of this particular diagram to the table that I skipped a few minutes ago? So actually, this diagram came from this table, the one that you have here. So this is, I'd like to lower this down. This is the liquid-liquid equilibrium data for acetone water methyl isobutyl ketone. If you use these two sets of columns, the last two sets of columns here, in plotting, the one that you'll be forming is this one. The rectangular diagram here, giving you the relationship of the concentration of the solute in the raffinate and in the extract layer for the horizontal and the vertical axis respectively. So where is it taken from? From the last two sets of columns in this table. So acetone distribution data. This speaks of this system acetone water methyl isobutyl ketone. In our case, it's not acetone. In this case here, it's not acetone that we're talking about, but rather acetic acid, because our A is acetic acid. So it's the acetic acid in the raffinate layer on the horizontal axis. It's the acetic acid in the extract layer on the vertical axis. Okay, this one is for a different system. Okay, we have a different, if we have a different system, we have a different set of values here. Now, so that's for the last two columns. How about this one? You may ask, how was this, how was this formed? Okay. The phase envelope on the upper triangular diagram that is paired on this rectangular diagram. How is it made? So you use in these three sets of columns here, the first three sets of columns, wherein you have the composition data written on top. You will use the MIK, the first column and the second column only. We're not, where is my cursor? I cannot see, wait, Kasa. We're not interested with water. So we're not interested with water here. Can't see my cursor, wait, class. We're not concerned with this one. We're not concerned with water. So the MIK is the vertical column, the Y, and your acetone is the X, This one, we're not interested with water. So if you plot these two, you'll be forming the phase envelope. This phase envelope here that appears on the upper triangular diagram. Okay, so that's how this particular pair of diagrams came about from a given table. So whichever of the two is given to you, you'll be able to find what you need to find. That is in terms of compositions only. But in terms of other requirements in the problem, there's really a need for you to have it plotted, especially in determining the number of stages graphically. So there's a need for you to plot what this G is, what this I is, and how you form this particular, you see these broken lines here. How do you form this? Actually, this is the tie line. How was it formed? Okay, I will discuss it in a little while. But before we go to that, do you have any questions so far with the things that we have covered in here? So none. So let me check if I still have. Okay, so this is already the first sample problem. Before I discuss the first sample problem, let's have a 10-minute breather. Then we'll come back at my time here is 1:35. So we'll have 1:45. So we'll have a break, a 10-minute break, then we come back to these problems here. So with our sample problem in here, with a mixture of 200 kilograms of 50 kilograms isopropyl ether, 20 kilograms acetic acid, and 30 kilograms of water, in a simple extraction equipment consisting of a mixer settler, we are to determine the compositions of the two phases that could be separated. Now, these two phases that can be separated is your raffinate and your extract layers. So your isopropyl ether is supposed to take out the acetic acid from the mixture, separating it from water. That way, water can be decontaminated with the acetic acid using the solvent isopropyl ether. So we want to know what would be the corresponding compositions of the raffinate and the extract layers for this particular problem. So the first thing that you're going to do in here is, of course, you should be able to find an equilibrium diagram for this system that is stated. So the system is acetic acid, water, isopropyl ether. So a different system will require a different equilibrium diagram. So that's number one requirement always. You should have an equilibrium diagram for your system. If you don't have a diagram, then you should have the table from where you can construct the diagram as I've discussed it a few minutes ago. Okay, now after you have already determined, look for the appropriate equilibrium diagram, then that's the time that you determine the composition of your original mixture. So very easy man lang mag-determine sa composition. So I will first use the Jamboard on how to determine the composition. So please take a screenshot of the problem. That way you can determine together with me the required information, especially the composition. Okay. So for our problem, we need to identify our given information. Actually, you have that same problem in, not the same, but comparable problem given as a sample in John Copley. So we have our original mixture. So we'll not just label it as M because you may think of it as the bulk phase. So the mixture contains or has 200 kilograms all in all of each of the components. So you have 50 kilograms of C. So I'll just place C, the isopropyl ether. Then you have 20 kilograms of A. And you have 130 kilograms of B. Okay, now, and that's it. It's placed in a mixer settler and then allow the two layers, the extract and the raffinate layers, to separate. So in here, So your mixer settler, it could be one mixer there. And then I'll show anyway the equipment later. And from in here, you will have a settling chamber. Wherein at the bottom part, you'll have the raffinate, and the upper part, you'll have the extract. Okay, in some equipments, this settling zone is part of the mixer already. In some equipments, it's separated. So I just place it in here. That way, it will be clear to you. From being mixed in here, then the mixture was allowed to come to equilibrium and the two layers to form separately. Then your extract is always on top and your raffinate is at the bottom. So we are required here of the composition of the extract and the raffinate layer. So I've just abbreviated it. So we need the composition of the extract and the raffinate layers given this particular information. Okay, now use the next slide. So the first thing that you ought to do is find the appropriate equilibrium diagram for your system. In our case, I will just for illustration purposes class draw here a diagram for the system. It need not be exactly the same as the system. I'm just drawing it here just for illustration purposes. So I'd like to draw here a triangular diagram. But in your case, you have to specifically look, John Copley has one for this system. Look for this particular equilibrium diagram for acetic acid, isopropyl ether, water system. So this is our 45-degree line. And let's say we have the curve in here, sample. Now, in the upper part, you'll have the phase envelope. So you have here your XE or your YA. In here, you have your XC or your YC. In here, you have your XA, the composition of A in the raffinate, so that's XA. In here, you have YA, the composition of A in the extract. Okay? We'll represent V as the extract layer and L as the raffinate layer. X for feed and raffinate composition, and Y for not extract, solvent and extract, so that it would be easy to follow. Extract composition. Okay, so it's the same actually diagram that I have shown to you a while ago for acetic acid, isopropyl ether, and water. In this case, our problem is water. What is our problem? Water. Did you take a screenshot of the problem? We have water, acetic acid, and isopropyl ether. So the same as the system that we have in the diagram, then in the PowerPoint slide. Okay, so the same thing. So I'll just go here. Now, next thing you do is determine the composition of the mixture. And the composition of the mixture represents the composition of the bulk phase M, which will later on form the two separate layers, extract and raffinate layers. So how do we find it? It's so easy. So you just simply account for XAM and Sige. X, ang B hindi na lang. So XCM. You will not determine B because we can anyway have it subtracted from the sum of these two. So how do we determine XAM? You just get the A here. So that's 20 divided by 200. So that would be 0.10. And for the C, you have 50. 50 over 200. So that would be 0.25. Okay, 1/4 of 200, so 25. So using this XA and XC, you go back to your diagram and plot it. So in this problem, this is requiring both analytical and graphical approach. We cannot really separate one from the other or have a totally analytical approach to this. So let's say we'll use the 0.2, 0.10, and 0.25. I'll just approximate, class, just for illustration purposes. 0.25, 0.10, 0.10, 0.25, somewhere here. Let's say this is my M, the bulk phase M. So what you're going to do, class, is this. This is trial and error, and this is how it's going to be. There's no other way to do it. So what you're going to do is, I'll use a different color. You approximate this one. Okay. You just choose one point, any point here at the bottom, or I will redraw my curve because it's really right on the horizontal axis. Wait, class. And make it rest a little bit above here. Okay. There you go. Now, I'll use a different color. You can choose either an upper point as your starting point. It doesn't matter. Or you can use a lower point as your starting point. Okay. So what you're going to do is this. Let's say I'll choose this one. This point here. This point that I have chosen, class, is my tentative raffinate layer composition. Okay, tentative. I say tentative because I will first check whether my tie line will really strike through the 3 points that I'm going to make in a little while. So what I'll do is this. With this point that I'll have, I'll go down here, continue until I reach the curve. Okay, then turn left. When you reach the curve, you turn left and stop when you reach the line. Then go up. Once you reach the line, go up. Okay, go up. Okay, that's it. Then you'll have this point here. Okay. This point is said to be your extract layer. Now, why is this a trial and error thing? Because the class you're going to check whether, okay, this one. I hope this could be seen. Whether the line that you're going to connect or the line that you're going to use to connect the E and the R, I'm just going to make it pass through. It's going to pass through the M. This line is your tie line. Remember a while ago, I said I'll discuss the tie line. So this is the tie line that ties the two faces that are already equilibrated. So in this case, this is your raffinate phase and this is your extract phase. There won't be any separation at all at the time when they are already reaching equilibrium, or they have rather reached equilibrium. So you have these two layers now. So once you have connected E and R, which you have started randomly R here, you go down, you go down until you reach the curve, you turn left until you reach the line, you go up and settle on the uppermost part of the face envelope, not of the triangle, of the face envelope. Connect this point with the raffinate that you started with. If the line that you're connecting the two passes right on M, which represents the composition of the original bulk phase, then this is your tie line. If this is your tie line, all you have to do is read. All you have to do is read the corresponding compositions of the raffinate layer here. Why is it not writing? Of the raffinate layer here and the extract layer. How will you read it? Raffinate is X. So this is your XA. You read what this is. And this is your, so I'll just label it in here so you would know. So raffinate, this is your XC, and this is your XA. Okay, for extract, this is your YC. Going down, this is your YA. You get it? But for example, you connected the E and the R, and it did not pass through the bulk phase M point. You have to redo everything again. You have to transfer it a little bit in here or in here, as long as the goal is when you connect the point that you have started here at the bottom to the point that you end here on top of the phase envelope, they will form a straight line together with the M. If not, then you redo everything again. So as to the answer to this problem, it really depends on how you look at it on the equilibrium diagram that you have. So it need not be that you will have all the same answers. You may have a difference in just maybe a 0.01 or a 0.2, a 0.02 or a 0.3 in your composition. It really depends on your plotting. Okay, so you should have this as the procedure. So I cannot give you the actual answer because it really depends on these points that you have placed in here on your equilibrium diagram. Do you get it? So that's it. In terms of the composition of the extract and the raffinate layer, that's it. You just simply read. What takes time is the process of really finding these two pairs of points in the lower part of your phase envelope and the upper part of your phase envelope, which when connected will form a line together with your bulk phase M point. Do you get it? Have any questions for now? Okay, so I think there's none, so we will proceed. So I'll go back to our PowerPoint slide. Okay, sige. Share. So that's share. Okay, can you see the sample problem 1 slide? So that's the problem that we have solved for now. Okay, so now we proceed to the next part of the slide. Now, it could be class. So that's our sample problem. This one is for partially miscible components. It could be that you have in the second triangular diagram example here is that you have this time not the components that are partially miscible, but it's the liquid pairs that you have formed that are partially miscible. So in this case, your phase envelope will be not one whole curve, but you have two separate curves forming at the bottom of your triangle and at the upper part of your triangle. You still have these tie lines here. You have these tie lines here, but you have one phase region that is being formed. So in the example that you could see in here, you have the solvent pairs B and C and A and C, which are partially miscible. So your B, let's say your water and your solvent pair is partially miscible with the extract phase, your solute and your solvent. The solvent and the solute that is already or your solvent that has already taken out the solute from the feed. So this is the phase that is being formed, and it is partially miscible with another phase which has your water. Most of the time B is water and your solvent. So they are both partially miscible. So this is your equilibrium diagram, triangular diagram that is on the upper part of your rectangular diagram if you have partially miscible liquid pairs. In most cases, class, we have this kind of scenario. We have this scenario wherein we have one phase envelope and producing only one phase region and one two-phase region. Not this one, but just in case you would be asked to identify what this is. So this is for a system wherein you have two liquid pairs that are partially miscible. Now, I'd like to discuss the inverse lever arm rule. I'm sure you know the inverse lever arm rule. However, this will not be used anymore as part of your methods in determining the solution to any particular problem that you will be encountering. So we will rely heavily only on material balances and the use of the equilibrium diagram like this one in getting the compositions that we need in the problem. We will not solve our material balance using the inverse lever arm rule. Now, what is this inverse lever arm rule? I'm sure this is not the first time that this was discussed to you, the inverse lever arm rule. This is partly graphical, so that is why I'm saying that I'd rather have you do it analytically all the time, because it will entail that you have to rely on what you have on the diagram and then read compositions based on the lines, the points on the lines that you have drawn in your diagram for your answer. Anybody who can tell me what the inverse lever arm rule is? Or if I will start putting here an example, you can finish it up. You can supply the missing information. I'm just checking if you recall what is the inverse lever arm rule. So if you use the inverse lever arm rule here, let's say I want to know the L, or why is this so thick? Wait, class. Okay, you have, let's say right here, you have the L over V ratio. Let's say I want to know the relationship between the L and my V ratio. The V is the extract and L is my, for example, my raffinate, in this case, the liquid phase. And this is the, of course, this is liquid phase, but we represent it as the extract based on the illustration that I have here. And M is my bulk phase, okay? M is my bulk phase. I have these two phases. Let's say in here, I have my feed. Based on the illustration, I'll use it. And this is my solvent. So in terms of the ratio of extract to raffinate, then the V will always be extract, raffinate will be the L. So V and the L, and this is the corresponding bulk phase M, the product of these two in this, let's say, mixer settler type of extraction equipment. And this is your bulk phase M. Now, using the inverse lever arm rule, if I want to know the value of one given the other, let's say, for example, I want to know the extract that is formed, the amount of the extract that is formed given the raffinate amount. So how would I use the inverse lever arm rule in here? That is, if you can still remember it or if it was covered to you. How will inverse lever arm rule here work? Let's say, for example, I'll just cut this one. I'll just place here a hypothetical value. Let's say this is 12 and this is unknown. I don't know that. How will I use inverse lever arm rule based on the illustration that I have here for me to know the amount of the extract formed from the raffinate value of 12 using the compositions of the points that I have here on the diagram? That is if it was discussed to you. But when I was a student at this part, I know already what inverse lever arm rule because it was already discussed in my other subject. Would you know what inverse lever arm rule is in this case? Anybody? How will it be used? I have here compositions of the points. I have here the extract, and this is the raffinate layer. These are the mass fractions. You can see here mass fraction of A, mass fraction of C. This is for the extract. So you see YA and YC. This is for the raffinate because you have XA here and XC. Inverse, from the term inverse lever arm, how will you use the coordinates of the points that you have here? By any chance, was this discussed to you? Who can say outrightly no? We don't have any idea. Or you don't want to say because probably it was discussed and you forgot. Because I will still ask teachers if it was really covered or not. Okay, so this is how you're going to do it. So no one will confirm whether it was discussed or not. You can either use this parts of your triangle. I have two triangles actually. Or I can use this part here, the vertical. I'd like to use this one. If it's inverse lever arm rule class, this is where my L is. My L is in here, and this is the triangle where my L belongs. And since this is the triangle where my L belongs, I should be using the other triangle. As such, it's called the inverse lever arm rule. So what I'll do, I'll get the length of this particular side of my triangle. How will I be able to get that length? So that would be coordinates XAM or X sub AM minus YA. X sub AM minus YA will be the side of this triangle. Where did I place it? Oh, sorry. It should be on the L because it's inverse lever arm rule. This is where L is, so I'll be using this one. So I'll write here XAM minus Y sub A. So then, I'll erase it. For the V, since my V is in this triangle, I'll be using this one. So then that would be, I'll be using the length of this side. So that would be XA. That would be from here to here minus XAM. And that's it. I'll be able to find the value of the extract layer knowing the raffinate layer, using the compositions here and the triangles that I have made out of these compositions of the dots representing the faces. This one is for the raffinate, this one for the bulk phase, and this one for the extract. You can have another one and use a different color using the vertical axis this time. So I'll use green. Let's say in the vertical axis, let's say I'll make another triangle here. I'll use this one. I'll have that and this one. So I can place here. If I want the V is part of this triangle, so I need this one. This is what I need, right? So that would be from here to here, that would be XC. I need the V, so I'll place it here. That would be XC, XC minus XCM. Where is that XC minus XCM? This is this side here. It's the side for the L. I place it on the V because of the inverse lever arm rule. Okay, vertical. Now, since now I have the L, then I will be looking for this one. So this would be XCM from here to here minus YC. Do you get it? So using the coordinates of the points that I have in here, inverse lever arm rule, I'll be able to find the value of the extract that was formed. That's inverse lever arm rule. If you don't want to know about this and you're going to use purely material balance, that's fine. Material balance will also work. But since this is covered in your book, this is how inverse lever arm rule works. And should you be asked about it, you have an idea how it's to be used. Have any questions? No questions on inverse lever arm rule? Sige. So if there aren't any questions, then we'll have this cleared and we'll proceed with the next slide. Now, sample problem number 2. So the composition of the two equilibrium layers in one, this is already partly determined, class. These are the answers already. After doing the one that I've shown to you in the Jamboard. So for the extract layer, this is you have 4% of acetic acid, you have 2% of water in your extract layer, and 94% of your solvent. True, because this is the extract layer. This is the solvent-rich layer. So it's referred to in other reference books as the solvent-rich layer. Your raffinate layer is the water-rich layer. So the water-rich layer has acetic acid, which is 12%. Your water is 86%, and your solvent is 2%. So the original mixture contained 100 kilograms of A, B, and C, and has this amount of A on it. Now determine the amounts of V and L. Now, the reason why I've discussed the inverse lever arm rule before this problem is because you could use it. You can plot these points here. Rather, you can plot the points representing V and L using these coordinates. They are also representing coordinates of A and C in the equilibrium diagram, and then find the corresponding amount of the two. But still, you can also determine it using material balance. Okay, so we will use material balance in this case. So please get a screenshot of the problem so we can go back to it anytime. I'll get also a screenshot so we can go back to our Jamboard and use the problem that we have here. Okay, sige. So that's the answer that we have. So I'll go to the Jamboard again and continue. So let's say we'll go to, this is our 1. And this is our sample problem number 2. So based on our answer in 1, the solution in the book gave you inverse lever arm rule. It also gave you analytical method. So you have the choice, whichever of the two works for you, or much easier for you to follow. So in terms of the problem, you have this composition for the extract. So I need only the A and the C. B is not any more important to me. So A and C, you have 0.04. Actually, I only need A specifically, but nonetheless, I'll place here C. So you have 94. If you want B, then that would be the difference of the sum of the two. So 0.02. For your extract, for your raffinate, this is for your extract, the V. For your raffinate, your XA is 0.12. So your XC is 0.02. And your XB is 0.86. So true to its name, your extract is the solvent-rich layer, your raffinate is the water-rich layer. Okay, now we are asked, or by the way, what else do we have in here? I have placed the compositions already. You're given the original mixture, the M, the bulk phase, which is 100 kilograms. Let's say it's just 100 kilograms. And its composition in terms of A is 10%. So in this case, you are required to determine the amounts of B and L. So extract and raffinate layers. You are to determine simply the V and the L, or the amounts of V and L. Since you're starting with the bulk phase M, which is 100, the sum of this extract and raffinate layer should be also 100. It should not be more than that or lesser than that, because they're coming from it. So your bulk phase M should be equal to the V and the L. So this is your overall material balance. This is already 100. You have V plus L. So for now, you have two unknowns. So that's your first equation. Now, you can do component balance on A. On A, you just have it patterned in here. Now, the question, why specifically A? It's because your problem give you a decomposition of the bulk phase in terms of A. If we're referring to the original problem, which has 200 as the original amount, and the compositions we determined are actually in here. If it's still 200, then we can go back to this one and use the compositions that we solved, like this one, in determining the amounts, specifically of the extract and the raffinate layers that are formed. So I intentionally changed the amount of M, the bulk phase M, to 100. That way, in terms of material balance, you will see that you will place here 100, not 200. Now, when you do component balance on A, you can even do component balance on C. You just use the C composition here, which is 0.25. Okay, you don't use the 0.10 because that's for the A. So in this case, since it's written here, we'll do component balance, overall component balance on A. So we'll have MXAM equal to VYA plus LXA. You just multiply the terms that you have here in the overall material balance by their mass fractions. So you have 100 multiplied by 0.10. Why am I doing that? Because it's the one that's stated in the sample problem. Then, you'll have here V, and then you use the YA based on the answer. So that's 0.04. And since I want the V and the L, I'll get here the L in terms of V. So my L here is 100 minus V. So your XA, 0.12 in the raffinate. So you have here 0.12. So you'll be getting here a V value. If you got the V value, just subtract it from the 100, you will be getting the L value. You can use also inverse lever arm rule, but the thing is you need to plot using the inverse lever arm rule. Okay? Now what would be our answers here? That's the V. What's your V answer? Didn't take me around 10 seconds to answer. What's your V?
25, Miss.
Okay, that's 25 and you have here 75. So these are your values. So this is the amount of extract and this is the amount for the raffinate. 25 kilograms and 75 kilograms for the raffinate. Okay. We will continue this next week. Hopefully, I'll finish everything concerning extraction next week. That way, the week after next, we'll have leaching. Do you have any questions?